This is the Smart Buildings Academy podcast with Phil Zito, episode 211. Hey folks, Phil Zito here, and welcome to episode 211 of the Smart Buildings Academy podcast. And in this episode, we are going to be talking about IP controls implementation. So last week, we had a live course called IP Controls, Design, and Implementation. It was all day long, and we talked about IT networking, we talked about IP controls, how to design them, and how to implement them. Coming out of that live class, got a lot of great questions from students, and so what I looked at doing in this episode was kind of highlighting on the topics that those questions related to and bringing those out, basically answering those in this podcast episode. As always, you can find all of the resources by going to podcast.smartbuildingsacademy/211. So in this episode, we're going to dive through what IP controls are. We're going to talk through the IP controls design patterns, and we're going to run through some implementation scenarios. So what are IP controls? IP controls, quite honestly, are, I would say, no different than regular field controllers, but at the same time, they are different. When they first came to the market, they really were no different than regular field controllers. All they were field controllers that used network interface cards and Ethernet plugs to connect them via IP instead of like MSTP or FT10. Now, what we're looking at with IP controls is that they actually more resemble like a plant controller. If you all are familiar with those hybrid supervisory field controller plant controllers that came out kind of around 2008, 2009, that was kind of their big year, their big push. And they had IOM on them, input-output modules, or they just had IO on them. But yet they had supervisory functionality. They had the ability to map in graphics. They had the ability to map in, to have trends, to have alarms, to have schedules. And they also potentially had field buses on them so that they could grab field controllers. That's what we're seeing with the majority of IP controls that are hitting the market. Now, there still are quite a few manufacturers out there who their take on IP controls quite simply is to use a BACnet advanced controller template. So if you're familiar with the advanced controller template, it has scheduling, it has trending, it has alarming built into it. But it's not got that full-blown supervisory with field trunk capacity on it. Now, on the flip side, we are seeing several manufacturers come out with these IP controllers that have field trunks built into them. So I've got some Edge 10s on my wall over there, and those actually have field trunk capacity. They have supervisory capacity. They're running Niagara inside them, so they act as a supervisory device essentially. And so you're seeing that. And the reason why is that you can now take a lot of the compute capacity and processing capacity that was required for a supervisory device, and you can fit it into a field controller at a price point that actually makes sense. So we're seeing that kind of migrate. Now, with that comes new implementation methodologies. So you can't just and this is one of the things that we really hammered in the class was you can't just go and put IP controls in a new project and expect to be able to wire them up like MSTP. And the problem with that is that IP controls are IP. And I want to really clarify IP real quick because people hear IP and they think Internet Protocol and they think Ethernet, and those are not the same thing. So Ethernet is both, I guess you would say, a cabling standard, RJ45 heads on an Ethernet cable, Cat5e, Cat6, Cat7, but Ethernet is also a layer 2 protocol. Now, with that being said, Ethernet is just one way of connecting IP controls. You also have fiber, you also have wireless, you also have mesh, you also have cellular. There's multiple different ways to connect IP controls to a network. So do not naturally equate IP with meaning Ethernet, although that is the most common form of implementation for IP controls. The reason I tell you this is because if you've ever built a building, or if you've been in a construction project, you know that the IT switchgear is usually the last thing that goes into the project. So you run into this scenario where you want to put in your IP controls, you want to get them all commissioned and communicating, but you have no switches to communicate with, no switches to connect to. And so we're seeing where you're either having to have some unmanaged switches, or you're having to have some industrial switches that you put in place to get the network up and working, and then you have to go and actually switch the IP controls over to the new networking gear once IT puts it in place. Also, with that, since IT tends to have their own addressing schema, you end up having to usually, sometimes, maybe not, readdress your IP controls. So not only are you implementing IP controls and you're implementing your own IP scheme and you're implementing your own switching and your own industrial switches, which industrial switches are basically just switches that are able to be in environments like a construction environment that maybe doesn't have temperature control, that maybe has unstable power, etc. And so you implement these solutions, and then you have to basically go and re-implement your solution. And a lot of people don't cost for that in projects. They don't go and look at what is the cost of readdressing, rediscovering, switching all our gear over to the new IT network. And then so because of that, they lose about 20 to 40 hours of labor on IP controls projects. Fortunately, that's something you learn on your first IP controls project, and you usually don't end up doing that again. Another question that was asked during the course was, what about ownership of the IT gear in the submittals? And that's a really good point. Well, I like to think that if we do a network riser with IP controls and we put it in our submittal, that everyone has enough common sense to realize we're not carrying the switches, we're not carrying the routers, they're not part of our scope. However, I will not leave common sense to my own fate, right? Because it never seems to rule out that, or never seems to not happen, that you put something into a submittal package and somehow, just because it's on your drawings, you inherit it. So we talked about, when you have your switches, when you have your routers, even though in my opinion it's obvious that we're not providing that, you should probably still say provided by others. Granted, you could also exclude IT switchgear in your scope of work and your scope letter that you are submitting as part of your bid. So that's just, something. I haven't seen it where people have held people accountable for providing switchgear and routers because it was on their network diagram. That's not to say that it couldn't happen. All right, so there's really three ways we're going to implement IP controls on our new projects. There's the star pattern, there's the daisy chain pattern, and there's the ring pattern. So the star pattern is your traditional design pattern that we've used to connect supervisory devices to switches, right? It's just an Ethernet cable, just a regular Ethernet patch cable between the access port on a switch and the network interface card on a supervisory device, except for in this case, it's the access port on a switch to the network interface card on your field controller. You'll typically use this if you're using a field controller for a plant system or maybe for a air handling system, and then you're going to use the field trunk on the actual controller to then connect via MSTP to other controllers that are maybe at terminal units. So you'll see that scenario right there. The great thing about this is that if you lose the link, as we'll see later in the other design patterns, if you lose the link, you're not really losing all of your controls, right? If you lose that access link, if for whatever reason it goes down, you're not losing all your controls. However, that being said, it is much more expensive because IT tends to charge people per the switch port, either from a capital perspective or an OpEx perspective, meaning they either literally charge you one time for the switch port or they charge you a continual fee. You usually being the facility team, not the actual BAS contractor. So just be cognizant of that. Additionally, with that, it tends to make IT people more happy, the star pattern, because they're only plugging one device into a port and they can track that device. There's a perceived increase in security when you only have one device on a port. I'll talk about why that's not necessarily the case when we get to the daisy chain and ring patterns, but it's perceived. So from a stability perspective, it's the most stable. It's also the highest cost and supposedly the most secure. Then we move to daisy chain. Daisy chain is interesting in that it's essentially like what we do with MSTP, right? We daisy chain from controller to controller, except for instead of having a terminal block that we basically stick the wires in and then we crank down our nuts on the wires so that they go and tighten them up, and then the wires are actually electrically bridged, right? They're physically connected. Unlike that, in a lot of controllers, they are logically bridged. What I mean by that is you have two network interface cards. One Ethernet wire comes into one, and then it leaves and goes to the other controller, and so on and so forth in a daisy chain pattern. Problem with that is if you lose power to a lot of controllers, if you lose power to them, since the NICs are not electrically bridged, the Ethernet cable signal on the Ethernet cable basically does not continue through, and so you lose everything downstream of that. Now we'll talk about ring architecture and how that negates that kind of, but be aware that a lot of manufacturers are aware of this limitation of IP controls, and so they're working on ways to basically create an electrical bridge when the controller loses power. But right now, a lot of manufacturers have that weakness, and so that makes daisy chain the least stable of architectures because you have no way of continuing along that link. It is perceived as less secure because you have multiple MAC addresses. Remember that a IP device is going to have a MAC address for their network interface card. That's the physical address. It's not to be confused with a 8-bit MAC address that you set via a dip switch on a field controller. This is a Ethernet MAC address, and it gives a unique address to each network interface card and ultimately each device. Now, here's the thing about that is on switches, you can actually set port maximum. So you can put a maximum limit of MAC addresses that can connect to that switch. And you can use MAC address sticky, which is a setting that allows you, at least for Cisco switches, to hard code that MAC address to that port so that that device can only connect to that port. Now, there is this thing called MAC address spoofing where you can find the MAC address and you can actually alter your MAC address in software. And so that is a way of bypassing that, and that can make port security insecure. But that's the same for star pattern too, right? So there's other things you can do to make sure devices are secure. You can use certificating, you can use authentication, etc. All that being said, as I tell many people all the time whenever they ask me about can't someone disconnect my controller and just plug in their device, I always say the bigger issue is not that someone can disconnect the controller and plug in the device. The bigger issue is that they're in the mechanical room, or they're on the roof, or they're in the ceiling, and no one is noticing that this person is in that space going and disconnecting controllers and plugging in their own devices. So the bigger issue is a FISEC issue, a physical security issue, rather than a actual cybersecurity issue. Now, with daisy chain, it is the least expensive because you only use one port. Some manufacturers will say limit of 16 devices. Some manufacturers will say no limit on their devices. The reality is you do have a limit between controllers of 100 yards or 100 meters, basically 300 feet for your traditional Cat 5e or Cat 6 cable. You do have that limitation between controllers. And like with anything, you do want to be cognizant of like running controllers forever, because the longer you run a daisy chain, the more impact it will have if there's a physical break in the wire. You know, if you have 200 devices on a daisy chain, which, Lord, I don't know why you would do that. I don't know why you would even do that with MSTP. I mean, that violates the standard of MSTP and RS-485 ultimately. But let's say you tried to do that, which some people do. That's a really bad idea, because now you're creating this singular link, and if anything breaks, you're taking down everything else. So it's just, in general, a bad idea. Usually what I like to do is I like to do a star pattern to an air handler and then MSTP to all the field controllers downstream. I really don't see the point of IP controls for terminal units. I just don't see the benefits at the cost point. Really, do you need graphics on your terminal units? Do you need the ability to run schedules and alarms and trends right at your terminal units? I mean, do you really need that? Like, I know it's nice, but really need that? And like some folks will go, but what about analytics at the edge, Phil? Do you really need analytics at your terminal units? I mean, really, we're not talking rocket science to look at damper position and projected flow rate and temperature and figure out if we've got a bad air exchange rate in our space, or if maybe we're not getting the right temperature from the air handler. I don't really see the case for analytics for terminal units. I get it for air handlers, predictive as well as fault detection. I get it for plants. I don't see the benefit for terminal units. Now, all that being said, with COVID and coronavirus and IAQ being like super duper important now, you might actually have a case for having analytics at the edge from a compliance perspective. Someone brought to my attention this reset standard, which I haven't read much about it yet, but supposedly it looks like well buildings, but with a spin towards COVID with a cross of lead. It's really a weird looking standard. But I'm just waiting for new standard bodies to come out and new legal compliance to come out around IAQ that will be requiring increased reporting, increased tolerances, no more of this like 2-degree deadband up and down on our terminal units for zone temp. And we'll see. We'll see if that happens. If it does, then it may make sense to have all that data at the edge. I don't know. I don't see it happening, though, in the very near future, especially with people not really reoccupying right now. All that being said, though, as I mentioned, star pattern is my preferred with terminal units coming off. However, daisy chain, you can do kind of where daisy chain to all of your rooftops, like have, 16 rooftops on the roof, 16 air handlers, daisy chain between those, and then terminal units off the MSTP trunks on those field controllers. That's a nice little pattern approach you can do. And then finally, there's ring. So ring is basically a complete circuit. And the premise of an IP ring is that if one path goes down, you can go back out the other port. So it takes 2 ports instead of 1 at the switch. It has increased redundancy. It still kind of has that low cost. And if one port goes down, then the other one will open up and allow it through. And what I mean by if it goes down, it'll open up, there's this thing called spanning tree protocol. And I feel like a lot of people in our industry don't really understand what it is. They just know that they have to use it for ring. But what spanning tree protocol is, so essentially on a local switch, we have messages that come out of your Ethernet ports. And if you've ever looked at a packet, which is IP, versus a frame, which is Ethernet, a frame does not have this thing called time to live. So on IP packets, you have time to live. And basically for every hop, so every transfer from switch to switch or switch to host or whatever that the IP packet takes, basically removes 1 from the time to live count. So the theory is that if an IP packet gets lost out in the wilderness of the internet, it eventually, that time to live will count down and that IP packet will disappear. Well, that's not the case with Ethernet frames. Ethernet frames will just keep circulating and circulating. So if you have a ring, which is basically a complete circuit, you have a loop now, and that Ethernet packet will come and go out a port and come back in a port and just circle. And each time it goes back out, it gets amplified until the point where you overwhelm that loop and you take the loop down. So spanning tree protocol introduces this thing called root ports and blocking ports. And basically what happens is you have a port that is open, all traffic flows out of that. The algorithm, the STA spanning tree algorithm, monitors that port status, and if it goes down, it brings up the blocking port, and it basically makes the root port go down again. What that allows us to do is that allows us to have a loop-free topology. So that's really important when you're dealing with ring, is making sure that either your controllers implement rapid spanning tree protocol, and I say rapid spanning tree protocol because spanning tree protocol can take up to 30 seconds to bring the loop back up, or to bring a port back up from a down state. Rapid spanning tree protocol can do it in nanoseconds, milliseconds, etc., depending on how you have the algorithm tuned. So either make sure your controllers support that or make sure that the switches have that enabled. That's just something to focus on. All right, so now let's go and look at a couple scenarios. So implementation scenario 1 would be a single rooftop unit with VAVs. So this is a pretty straightforward one. This is actually one of the neat things about IP controls done right. You could, in theory, on like a small to mid-size office building, take like an Edge 10 or an Edge 30, install it on the rooftop unit, wire it up, put your field controllers off of the field bus, and then not even use a supervisory device. Just put your graphics in that Edge controller, connect it to the network, and use that as a supervisory device. This is one of the most unused use cases I see with IP controls. Everyone complains about the cost premium on IP controls. They complain about the increased cost of Ethernet wiring, both of which are true. I agree. One of the benefits of IP, though, is the speed to download the controllers, as well as the ability to use it as a supervisory device in some of these small to medium jobs. So I highly recommend that you look at that, because that really gives you a lower cost point, makes you more competitive. So how I would architect this is I would put like an Edge 10 or Edge 30, depending on my IO count, and depending on like what compute capacity I needed and things like that, or something similar to that, right? I'm just using that because that's a very common product, and Niagara has a large market share, so most people know what it is. But I mean, it could be similar, right? And so once you put that in place, then you run your field controllers off of the field trunk, wire them up, and you're good to go. And that's it. I mean, pretty low cost implementation strategy that you can do all day that will keep your costs down and is pretty easy to implement. Then we have kind of implementation scenario 2. This is one that one of the students brought up in our course, which, by the way, will be at podcast.smartbuildingsacademy.com/211. You'll be able to find a link to that course. But implementation scenario 2, 30-story office building, air handling units, VAVs, chillers, boilers, etc., the whole kit and caboodle. So what I like to do here is I like to put some supervisory device in. And the reason why is in this scenario, I like to have a central supervisory device that acts as my single point of reference for graphics. I mean, in theory, you could go and actually have all these individual IP controllers and have graphics in each one and have your trends and schedules and alarms in each one. But that becomes kind of a pain in the butt for the end user, because when you think about this, right, you could have 2 air handlers on each floor, right? One on the east side, one on the west side. And you could have them then running loops to their VAV boxes that are on the floor. And you could have them basically stacked like that. And so if that was the case on a 30-story or 20-story office building, you're looking at like 40 to 60 IP controllers with their field buses going to their terminal units. And so that's 40 to 60 IP controllers that the end user needs to log into in order to view the graphics. Not very convenient. It would get really frustrating really fast to me. So what we do is we bring those into a supervisory device via, BACnet IP or whatever we decide to use. And we map all of those graphics into the actual supervisory device. Because, I mean, at the end of the day, if we lose connectivity to the IP controller in an air handling unit, if this is an office building and not a hospital, then, I mean, we're okay. We can go and run that thing in manual. Now, if this was like a hospital or a critical environment, I may recommend putting graphics in the IP controllers at the air handling units and making them individually capable of running their terminal units and their air handling units, but yet still mirroring the graphics in the supervisory device. So it's a little bit of redundancy, but it also enables us to still have that ability to go to the supervisory device for a single point of graphics. Additionally, right, our chiller and our boiler and our hydronic loop setup, we would want those on their own IP controls. We would want graphics in those IP controllers, and then we would want those mapped back into the supervisory device. All that pretty straightforward. I feel like any technician who has been in the field for about a year should be capable of laying this out and implementing it. I mean, it's not a terribly difficult implementation. Here's where people get hung up with this kind of implementation. If this was BACnet MSTP to a supervisory device or a series of supervisory devices, what you would do is you would have your supervisory device and you would go and have your Ethernet switches, and you would have your trunk links between those switches that are sitting in the panels, right? So you have the supervisory device or devices in a panel, and you have an Ethernet run, and all of these switches are basically connected to one another. And you might have like an unmanaged 48 port switch sitting in the MDF, and you call it a day, and you'd just be waiting for IT to give you a single drop, and everything be good, right? That's how you would probably set this up. With IP controls, things become a little different because now you have all of these IP controllers, and they're going to a supervisory device, and you can go and still do that with the switches. But now what you're going to have to do is you're going to have to go and have a lot more IP devices. So you're going to have more switches. So you're either going to have to make a decision. Do we increase our switchgear count? Do we go and put all this in either like an industrial switch or a or some sort of switch in maybe like a NEMA panel that's rated for the environment? That's one thing you can do. The other thing you can do is decide to use the IT network, which is what a lot of people decide to do. They decide to use the IT network. The problem is the IT network's not yet in place. So there's your conundrum. So if you are going and implementing this, you're either going to have to delay commissioning and final test until right about close to the certificate of occupancy when they start putting the IT gear in place, or you're going to have to implement your own network. So that's something, and like I said, it's not something you don't already do, right? You already implement a network. You just don't implement it at this scale. And so just be cognizant. This is where I feel like a lot of people get tripped up is they see more IP addresses and they feel like it's harder. It's not necessarily harder. It's just you're scaling it larger. You're using more switches. You're possibly using multiple subnets, or you're using larger subnets. So as long as you understand subnetting, as long as you understand switching, as long as you can set up a basic router and put routes between the different VLANs or subnets that you're creating, then you'll be just fine. But if you can't do that, then you're going to find yourself in a world of hurt. All that being said, though, these aren't terribly difficult things to implement. So I feel like a lot of people overthink IP controls, and they don't realize that it really is very similar to what they've been doing in the past. The problem I run into, and the reason when we taught the live class, we spent the entire morning teaching IT networking, teaching subnetting, teaching people routing, teaching people access control lists and firewalls and RSTP and spanning tree protocol and all of that, is because if you don't have that down, going and creating an IP controls design or implementing IP controls is extremely difficult. If you do have that down, it's actually relatively simple. So that's my advice to you. I hope this helps you kind of demystify IP controls, give you a perspective of how you would use IP controls on your projects, give you the different architectures that you can use for IP controls. All in all, not too terribly bad, pretty decent, pretty easy. If you have any questions, do not hesitate. Please go to podcast.smartbuildingsacademy.com/211. You could check out the IP controls and implementation course. It's fully online, self-paced, and you could check that out. It'll be in the show notes for the episode. Thanks a ton for listening, and I look forward to talking to you again next week. Take care. Take care.